Imagine that we know the trajectory of an object. This gives us information about the position of the object as a function of time. It is very useful information, but often it is not enough on its own to describe a physical system in its entirety. In the field of kinematics, which studies the motion of bodies, we need velocity and acceleration in order to have more complete information. And it's in this, and in many other contexts, that a very powerful tool from mathematics comes to help us: the derivative. Today, we will see what a derivative is both logically and mathematically, how to apply it to physics, and how it builds one of the most important equations of all. Given a function f of x and a point x0 where the function is defined, the derivative of f at x0 is defined as the limit as x tends to x0 of f of x minus f of x0 divided by x minus x0. To understand what this means, let us split the formula into two ideas. The first idea is the difference quotient. This ratio compares how much the function changes with how much the variable changes. In the numerator, we have the change in the value of the function, f of x minus f of x0. In the denominator, we have the change in the input variable, x minus x0. So the difference quotient tells us how much the function changes compared to the change in x, but this is still an average change between two different points. The second idea is the limit. By taking the limit as x tends to x0, we force these 2 points to get closer and closer. The distance between them becomes smaller and smaller. In this way, the average change becomes an instantaneous change. So the derivative answers a very precise question. When x changes by an extremely small amount near x0, how does the function f react? This is the mathematical nature of the derivative. It is a tool that measures the local variation of a function. And now we can understand why this is so useful in physics. Let us look at the following example to understand the usefulness of the derivative. Consider this function. S of t equals s0 plus v0 times t plus 1/2 at squared. Here, t is time, a is the acceleration of the body, and s0 and v0 are respectively the initial position and the initial velocity of the body. This is a fundamental equation in kinematics for the study of uniformly accelerated motion. In other words, this equation gives us the position of the body as a function of time when the body accelerates constantly. Now, imagine a body at rest, that is, with s equal to a constant. Then imagine perturbing this state by changing its position. In order to do this, the body has to move, which means that it must have a certain velocity different from zero. More precisely, this is an instantaneous velocity, because we imagine doing this in an extremely small interval of time, which in physics is called infinitesimal. What we have done is essentially applying the derivative to position with respect to time. The result is precisely velocity. Instantaneous velocity is therefore defined as the derivative with respect to t of the position s. This means that, by differentiating the equation s of t with respect to t, we obtain the equation for v of t. More precisely, v of t equals v0 plus a times t. Now let us apply the same reasoning again. A body with constant velocity is perturbed, that is, its velocity changes, which means that an acceleration appears. By reasoning in the same way, the instantaneous acceleration of a body is defined as the derivative with respect to time of its velocity. By differentiating v of t again, we obtain a of t equals a. Notice how this equation no longer contains the variable t. At every instant, its value is a. In fact, at the beginning, we assumed that the body accelerates with constant acceleration. This is a simple example of how, starting from one piece of information, the position, we are able to obtain two others, velocity and acceleration. And all of this by computing a derivative. One might ask what happens when acceleration changes. To define the variation of acceleration, we use a new variable, and this process can be repeated again. In fact, we enter an infinite chain of quantities, each one describing the variation with respect to time of the previous one. But these are usually ignored for a series of reasons that we will discuss in another video. For now, it is enough to know that classical physics is essentially based on the concept of acceleration, and therefore we usually do not need to go further. When we say this, we are mainly referring to one equation, F equals m times a. The total force applied to a body is the product of its mass and its acceleration. This is the second principle of dynamics, introduced by Newton, and it is an equation that appears practically everywhere in physics. Here, acceleration is the key, and, as we have learned, we can write it using the derivative. If we wanted to always refer to position, we could write F equals m times d squared s divided by dt squared. Here, the two number 2's indicate that we are differentiating the position twice. Because, as we remember, acceleration is the derivative of velocity, which in turn is the derivative of position. But in reality, physicists often prefer the form F equals m times dv divided by dt, that is, with only one derivative. The reason lies in the nature of the derivative. The operator is linear, which means that it has a set of properties, including the possibility of taking constant terms out of it or putting them inside it. Mass is a constant term, so it is correct to write both m times dv divided by dt and d of mv divided by dt. In physics, mv is known as the momentum of a body, a quantity used in the study of collisions to understand how bodies collide with each other and how their energy is transferred during the phenomenon. By combining all this information, the second equation of dynamics becomes F equals dp divided by dt. This is the most practical and general form of the second equation, and it is also called the Cardinal equation of dynamics. There is also another variant, m equals dl divided by dt. Here, m is the moment of the force, and L is the angular momentum of a body. We can see these two quantities as the counterparts of force and momentum in the study of rotations of bodies instead of translations. Together, these two equations are almost always sufficient to study the entire dynamics of material points or rigid bodies, and, essentially, they only require us to compute two derivatives. This should make you understand how much physics is based on the concept of infinitesimal variations of a variable. And with this, we have finished. We have seen some mathematics with limits and the difference quotient, and we have seen the importance of the derivative both in kinematics and in the construction of the cardinal equations. If you enjoyed the video, consider subscribing to the channel and leaving a like. Thanks for watching, and I will see you in the next video.